All right, Matthew 24:29. Immediately after the tribulation of those days shall the sun be darkened, and the moon shall not give her light, and the stars shall fall from heaven, and the powers of heaven shall be shaken. Welcome to Bible Smack. All right, so this is New Year's Cosmology, class number 11. Handling my light work. All right, so today, first of all, let me make a correction on class number 10. We had Dayton Miller, not Davies, who conducted the Michelson-Morley experiment to find 10 kilometers per second. Okay, in other words, to find the ether wind. All right, and so basically, now the first thing that we learned about today is we're going about these powers and angelic forces. The Bible has that concept of the powers and the angelic forces. The naturalistic system of philosophy, we usually think of things in terms of there's these, laws of science that are just there for no reason, and it operates like a machine even though it's not supposed to be intelligently designed, and all this other weird gobbledygook, right? So basically, when you look at some of the old Catholic astronomers, and a Catholic Latin scholar kind of showed me some stuff, basically you find that they describe angelic forces behind the movement of stars and other forces of nature. And so what that does is, instead of God operating a mechanism or a machine, God is operating a corporation. Okay, so everybody has a job, and if he wants everybody to stop the job, he just tells them to stop. If you had a machine, it would just go according to program, and then it could all mess up. And that's, kind of like the way environmentalists think about the world. It's like, oh, you could all mess up all of a sudden, Oh, no, you use paper instead of plastic. Well, anyhow, in physics, they've determined 4 fundamental forces. And so, what are these forces? Well, you have weak force, strong force, gravity, and electromagnetism. And, the strong force would be the solidarity in the physics, and the weak force would be kind of the emptiness. But basically, when you have these others, you have gravity and electromagnetism. And I'm not a physicist, so I'm just giving you a basic explanation, but these are the two that we want to really focus on today. Gravity, and I was watching Neil deGrasse Tyson talk about it. Somebody asked him, what is gravity? And he said, next question. Gravity has not been universally defined yet. Even though we see gravity, we know gravity. I know what gravity is. When I do this, and I fall back down, that's gravity. So basically, we have some idea of what it does, but we don't know what it is. So basically, you had some different schools of thought. I think what you see with Albert Einstein, usually the way he thinks of gravity is that you have, this inclusion of space, and then you have a lack of space, or let's say mass, the mass and the lack of mass, and it moves. And so basically, these are, this attraction kind of comes from this need of mass. But the way I would define it, and I'm going to define it the way a lot of guys who operate in a system called the Electric Universe would operate it. A really good guy to look at. Now, I'll link his stuff on his theory of gravity. Basically, that it's a microscopic electromagnetism. Now, let me not get too far ahead of myself. We talked in earlier episodes about what the universe is made of. And you have dark matter and dark energy, and how even though these are explanations for things, they're not actually things that we have observed, whether it's spectroscopy or particle colliders, we just haven't found it. So maybe it's not really there. People are pretty quick to say, I can't see God, so I don't believe in him. Well, I can't see dark matter, so I'm not going to believe in it. But basically, what about the visible universe? Okay, that's supposedly, the Big Bang universe is 95% of this stuff we haven't seen. But the visible universe, what we've actually seen, is 99% made of plasma. Plasma is the fourth state of matter. It's a superheated gas, and it has very electromagnetic qualities. Now, the stars, the light, the heat, all the things that we observe, 99% of it, of what we observe in the universe, is plasma. What is plasma? It's what you're looking at right there. Okay? It is that screen. A good example is this screen that you're looking into right now is made of plasma. Now, as I said, plasma has electric or electromagnetic qualities. Well, what's the difference between electromagnetic energy or force and gravitational force? Well, it's 10 to the 36th power. So that's 10 with 36 zeros. More than gravity. So this is a huge shift when we kind of understand the universe. If the universe is covered in all this plasma, then there is power. 10 to the 36th power is stronger all over the universe. Now, you have to understand something when we start talking about gravity and physics, why this has not been a big concept. You start off in history and you look at Isaac Newton. Now, Isaac Newton came around in the 1600s. It'd be another 150 years before Ben Franklin discovered that lightning, or just theorized, there's a lot of debate about it, but the fact that he discovered that lightning was electric. So for them, there's not really a whole lot more than little aberrations that they would understand being electric energy, and so it just wasn't coming to the mind very quickly those many centuries ago. So when Newton understood the universe, he really, looked at everything through the lens of understanding this discovery of gravity. And the concept of gravity, and the universe must therefore move by the power of gravity. Now, others came around later, but you see, Newton's concepts would then lead into quantum mechanics. And when we start looking at, checking out the size of all these different things and the qualities and stuff like that, that's when we start getting into these calculations based on gravity. And then all of a sudden we see forces that are not explained by our gravity. So we say, well, that's a different gravity. And then we start calculating all these things. And it becomes a big mathematical puzzle. And it takes a genius just to understand it. But, that's where Einstein came in. He came into this more physicality universe based on gravity. Well, down the line, before Einstein came along, there was a guy, James Clerk Maxwell, and he finally discovered electromagnetism. And when he discovered electromagnetism, even his understanding of things, he started to see that the force of electricity was much greater, and even the world, the earth itself, had an electromagnetic field. And eventually, this relation with the physics of the universe would be universal. But there's been this duality with science in the physics realm. Science has kind of gone on with this assumption of the gravity-dominated universe, and then we get into the quantum universe and all those things. But the guys who were involved in electricity and electromagnetism, they always had an opposing view. And so the first guy to say, hey, maybe gravity might be part of this electromagnetism system, and maybe Einstein's wrong, is, and who would do it? Who would challenge a genius like that? Another genius. Nikola Tesla. You may not know his name very well. You might, if you're into science, you might hear a couple things with the name Tesla on it. But if you study the history, you find out that Nikola Tesla was one of the greatest inventors in the world. A lot of his inventions were kind of smuggled into his boss, Thomas Edison. And so a lot of things that he did not get credit for. But he had many things. Radio waves, he developed alternating currents. He had the AC and the DC. Now, I can mix that up, okay? And I'll admit whenever I can mix something up. But you can get it straight. But, basically, Thomas Edison had one of them. I think Edison had the AC, and then therefore Tesla had the DC. But basically, when we look at Nikola Tesla, he had discovered things, even like this phone right here. He had discovered wireless technology and had it in the 40s. He just didn't have anybody to call. But basically, he had discovered all these incredible things, but he was going against the grain. He was going against the system. And so people didn't respect him, and the government confiscated all his stuff. But he had a problem with Albert Einstein, and here's the core difference. He said that, you guys with this new cosmology and stuff, or I don't know if it was new physics, Albert Einstein, it's all about mathematical wizardry. Science is about experiments, what you see with the experimental evidence. And so that's the heart of where Nikola Tesla and this breed of people came in. And there was another guy later on, back in the 70s, Hans Alfvén. Hans Alfvén was a German, I believe he's a physicist. He got a Nobel Prize in electromagnetism. Okay, he was a Nobel Prize winner. And he started to realize that, hey, look at this plasma. The plasma's got to be stronger. It's got to be affecting things. Okay, so, with all this power, it has to be a major force. And so both these guys, and they looked at gravity and said, maybe gravity's a minuscule force of that. And so with their theory of gravity, and Walt Thornhill is a good guy to kind of go to about that, they would look at the Earth, and what they would see is that with all the Earth's mass, the electrons would have their negative energy surrounding the Earth, and that would bring about the gravity. And then the positive energy would coalesce in the middle, and that's why the Earth would hover. So that's their electromagnetic understanding. And so, a lot of these guys, they would go by the math, and they wouldn't go by the experiments. They wouldn't go by these evidence and kind of say, look, and let's do this, and ha-ha. So we go back to another concept, the black hole. Now, the black hole was, really built the ground for quantum physics, because they noticed that there's all this energy that's seeping towards this area, but you know what? They never saw any black hole. And they assumed that that energy was gravitational. But that gravity has been found, the math just hasn't worked. Because look how weak gravity is compared to electromagnetic energy. How is gravity bending space and time? And that's what you get when you get with this kind of universe of these black holes. Now, in recent years, they have had mathematicians find this out, and even Stephen Hawking agreed with the mathematical improbability of the black hole. But we've been discovering, based on their reasoning, bigger black holes. We don't see them. But these theoretically have to be around because there's all this energy. There's all this energy spinning these galaxies. And so they're finding it in the middle of these galaxies, in the middle of our galaxy. And they're saying, well, they're black holes. They're giant black holes. And so the next step that they've taken recently is they say that really recently, although I think this idea has popped up over the years, but really recently they've said that there's these two black holes within the galaxy, supermassive black holes, so it's impossible, but now it's supermassively impossible. But now you got two supermassively impossibles spinning around. And because of that, it's making these waves, and therefore they have now found the gravity waves that Albert Einstein predicted. The only problem with this idea is that the effects that they're actually seeing, besides all the rational stuff I just brought up, the effects that they're seeing are effects that we've found elsewhere. Now, I want you to look here. See if we can get that big enough for you. Now at the bottom right here, that is what they're saying is a supermassive black hole. Okay, it's the same effect, but actually that's plasma. This is plasma density. And they'll also show you this effect over here, classic electromagnetics. And what they're finding is that's Birkeland currents. And when they see these spinning, see the spinning energy in this one, when they're seeing these spinning galaxies, they're seeing the same effect of the electromagnetic energy. So you find these Birkeland currents. Now, I've argued before that these galaxies might not be as big as we think they are. Okay, that was in class number 8. And so what if they are manifestations of electromagnetic energy? What about the quasars? What if the quasars are plasma? There was a fellow who argued this point. Let me see if I can find him. Jurgens. Ralph E. Jurgens. And basically he argued that maybe the stars are electric. What would that be like? Well, they argue that they find neutrinos, manifestation of neutrons, coming from the sun. But the question is, are these coming from the inner core of the sun, or are they just coming from the outside as the outside makes fusion because it's so hot? But in reality, these suns and these stars are all connected together in an electric universe. I kind of think about it like if you're looking at a Christmas tree. You have all these cords that you don't really see very well, and then you have the Christmas tree with all the Christmas lights. Perhaps all of our stars are connected electrically. Now, they have talked about quantum wormholes. See, all these manifestations are explaining gravity, but actually, you can just flip them around because you're just, when you look at a telescope, can you see the difference between gravity energy and electric energy? I can't. So, when we look at that, we look at the sun. We found recently electromagnetic portals that connect the Earth to the sun. If they're connecting it, now it's like a wheel. They kind of reconnect and connect and connect and connect. But basically, there is this electromagnetic connection between the Earth and the sun. And then we look about, as I said, there's a theory with the stars. And then the comets. Recently, they had a Rosetta mission with the comets. And the comet that they found was about 2.5 miles across. They said it looked like a rubber ducky. It looked like an asteroid when they got close to it. Okay, they usually think of it big snowball and it's just throwing snow everywhere. When they got close to it, it was a rock. It was, now I do believe it had some ice and water underneath it, and that could burst out occasionally, but for the most part it was a rock. And they landed the probe onto the Rosetta Comet, and what they found on the comet were dunes or piles of dust. Why does that matter? Well, when you have that weak gravity energy, it should not be enough to keep the dust on. The dust should be flying off. But yet, there it was. Piles of dust dunes. And when you see them report on this in the Rosetta mission, they're kicking themselves. I mean, it is just really sad looking. But basically, the only energy that could explain that is the comets. And so now we see all these different signs of electric manipulation, electric energy. We have an electric universe. We have a plasmatic universe. And as I explained in my one on the biblical, I think it was number 6, class number 6, basically God creates the earth, and then he's got heaven, okay, and then he's just got this light, and it's like evening, morning, and there is no sun or stars. That comes later. Now, the plasma in the universe could be a combination of the light and the waters, because the waters were separated from the waters. And you have two areas, essentially. You have this dividing canopy, but then you also have this stuff stretching out past the stars. So perhaps those gases are from that stretching out. But essentially, what we have is we have a universe. Okay, we talked about the ether of the universe. Now we're talking about the plasma of the universe. And we have all this energy in that membrane. Okay, it's all connected now. Now we have the ether. Now we have the connections of the electricity. And it's all flowing together. The question is, though, what about the light problem? Remember the light problem? We talked about that when we talked about busting the Big Bang Theory. What do we do with it? Well, one of the creation scientists was a guy named Jason Lisle. I had the honor of meeting Jason Lisle several years ago at a little creation conference. He was just getting ready to get his degree, his doctorate in astronomy, his PhD. But basically, Jason did some research, and he started studying some things Einstein said about light. And one thing we don't really think about with light is the only time that we ever measure light is when it's already reflected. Now, if the light hits and it bounced back, is there a time frame? Could that have lowered the energy scale when it hit? Theoretically, and I think even Einstein admitted, it could be that light, unreflected, is instantaneous. And there's not really a whole lot of ways to disprove that it's instantaneous. Now, we usually think about light going across an array. Of course, we also know that it travels in waves. But how can that instantaneous light be? It's part of that massive membrane with the ether and the plasma. Okay? All of the heat, all these manifestations are electric. Okay? The light of the universe is electric. The heat, the cosmic microwave background radiation that covers the whole universe, it's all electric. And so what we see is it could be all part of this major membrane. But let me also tell you something that's kind of interesting about the light. Now, certain places, MIT, I think Harvard, they've had some astrophysicists who've learned how to, and I could have that wrong, but they've had physicists, we'll just make a looser word, who have been able to stop light photons. Okay, these things are just zipping past. All of a sudden, they've been able to slow it down till it stops. Which is kind of funny because Einstein said the light was a constant. It never changes. That's part of his whole construction theory of relativity, right? But hold on, the light stopped. And then Barry Satterfield, before that though, he did some research, and this was peer-reviewed. Barry Satterfield did some peer-reviewed research, and he found that the mathematicians and astronomers that have calculated the speed of light over the many years, which I believe the speed would be 189. I could get that mixed up, 186, 187, but we'll say 189 million miles per second. Basically, he showed how there's slightly less, or no, excuse me, the speed of light was faster when it was first calculated in the 1600s, and that it slowed down over the centuries. Now, it's not, we're talking millions of miles per second, so it's obvious that it's not that much, and especially if we observe that anisotropic convention, but this gives more light to the anisotropic convention because the light is changing when it comes to reflective light. The energy is slowing down, which is fine because there is something we call the second law of thermodynamics. And so these things are slowing down. We also found something, I saw once the CERN, C-E-R-N, which is where they have the particle collider and stuff, they actually noticed a photon teleporting. I believe it was 15 feet. It was basically traveling at its speed and stopped. And 15 feet later, and we don't have 15 feet of this board, but 15 feet later, pops up again. How does it teleport? What about this? Think about this screen again, okay? And if you broke down that screen, everything would break down into pixels. What if the photon was exactly where it was and it never moved? What if the light is already mapped out and stretched out throughout the ether, throughout the whole universe? and these pixels are operating independently. You see how long it took to zip across? No, it all came together. It all developed a picture. Let's see here. See that? What if the whole universe is in operation like that? Well, obviously, there would have to be a designer, but you know what? It would work. And if it works, then the light problem is solved. The light problem the Big Bang can't fix. Because they're going to tell you about, what, 11 billion years? And they've got 32 billion years across with each star on the opposite ends, all coming together at the same time. That's breaking their speed of light. And so this is solving their problem. It's solving our problem. It's God saying, let there be light. All right, we'll see you a little bit later on New Year's Cosmology class.